This video is on chapter 16, basically thermodynamics, delta G, delta H, delta S, spontaneity, entropy, and free energy. Spontaneity and free energy are related to delta G. Entropy is S for entropy. And you've learned about all three of these a little bit. Now you're going to learn more. First we'll learn about spontaneous processes, and then we'll talk about entropy. So here's a definition, if you will, of spontaneous process. This is a process that occurs without having to add energy continuously. You may sometimes need a spark to ignite the reaction or whatever process we're talking about, but then the process continues on its own. So you might need a spark, and the whatever process could still be spontaneous, even if you need a spark to get it going. Entropy. We've already learned about entropy. It's how many different microstates a system can exist in, and the symbol is S. And we learned in the past the entropy of a solid is less than the entropy of a liquid, which is less than the entropy of a gas, because a gas can have more microstates. If you have the same number of molecules in your gas, you have more microstates than a liquid, which has more microstates than a solid. Also, as pressure increases, if you have the same volume and pressures going up, entropy would go up because you have more molecules in there. As temperature goes up, you'd have more entropy because the amount of energy that each different molecule could have or could transfer to another molecule increases. Okay. Second law of thermodynamics. Entropy of the universe has to increase if any process is spontaneous. It's important. In other words, if delta S is greater than 0, that would drive a reaction in the forward direction. It would cause a reaction to be more spontaneous. However, entropy is not the only thing that defines if a reaction would be spontaneous or if a process is spontaneous. It also depends on enthalpy, and we'll talk about that a little bit later. For now, you just need to know positive delta S's drive reactions forward. Doesn't necessarily mean the reaction is spontaneous, but it would drive the reaction toward being spontaneous. Positive delta S. All right, free energy. Gibbs free energy, G. First off, Gibbs free energy is how much work you can get out of a system or a reaction. And Gibbs free energy tells you if a system can be spontaneous or not. It depends on the sign of delta G, actually. The sign of delta G, not just G. There you go, fix that. Okay, we have the equation. Gibbs free energy is enthalpy minus temperature times entropy. And we'll put deltas in there a little bit later. Some important facts here. If delta G for a reaction is less than 0, the reaction is spontaneous. If delta G is greater than 0, the reaction is non-spontaneous. If delta G equals 0, the reaction isn't going to do any work. You don't put anything into the reaction to get any work done. To make the reaction go. The reaction is just at equilibrium. You can't get work out of it. You don't put work into it. Okay. Let's go back to entropy. We're going to talk about different entropy situations. Okay, so now think about delta S. We learned previously that gases have more entropy than liquids, have more entropy than solids. So the more gas you have, the more entropy you have. So if you have more moles of gas in the products than reactants, and delta would be products minus reactants, there's more moles of gas in the products. So the products have more entropy than the reactants. More minus less, is that positive or negative? We're going for positive or negative here. Okay. Positive minus something smaller than that positive gives you a positive number. Delta S is greater than 0 or positive. Think about if you're dissolving a solid. Is entropy going up or down? You have a solid going into aqueous ions. I'm going to show the answer in a moment. Entropy is increasing. Delta S reaction is greater than 0 because aqueous ions have more microstates possible than a solid. Okay, I'm just going to put these all down. You can pause this. And I'm going to pause right now and put all the answers up. So you should do these on your own right now. Okay, here are your answers for these. If anything is confusing to you, send me a quick email. I'll go through this very quickly though. Okay, sodium melts. So we have a solid going to a liquid. Liquids have more entropy than solids, therefore entropy went up. Delta S is positive. If entropy goes up, delta S is positive. If entropy goes down, delta S is negative. We have a gas going to a liquid. Entropy went down, negative. We have a liquid going to a solid. Entropy goes down. Entropy is less than delta S is less than 0. Liquid going to a gas. Entropy increased. If delta S reaction is positive, entropy went up for the products. All right. Predict the sign of delta S reaction for each of the following reactions. You can pause this and fill it in. I'm going to talk a little bit and then show you the answers. If there's no gases, you just have to think about what makes sense here. If there are gases on both sides, you have to compare the total moles of gas. You ignore solids and liquids if there are any gases. You just look at the total moles. And make sure you're looking at the total. So this 2 and 1, that'd be 3. We don't say there's 2 here because there's 2 different chemicals and only 1 here because there's only 1 chemical. Okay, so here's your answers. Hopefully you paused it. Pause it. Put in your answers. Here's the answers. I hope they're right. They should be right. Okay, moving on. Free energy and chemical reactions. You've seen this equation right here before. Delta G of a reaction is products minus reactants. And we have a new equation relating delta G, Gibbs free energy, to enthalpy and entropy. So notice, we already said Gibbs free energy, if this is negative, the reaction is spontaneous. That was right back here. This is very important. This stuff right here is extremely important, all 3 of these. So less than 0, spontaneous, greater than 0, non-spontaneous. Oops. So where did we go? Oh, there we are. Okay. So if this is less than 0, we have a spontaneous reaction. So let's think about what drives reactions. Well, should this be positive or negative to get a negative delta G? Negative! Exothermic reactions drive reactions forward because they make the reaction more spontaneous, so negative delta H. And what sign should delta S be? We have minus T. T is never negative. We use temperature in Kelvin. Delta S should be positive. So exothermic increase in entropy, that's what drives reactions forward and give us spontaneous reactions. And then we also have this delta G is products minus reactants. Students often get confused. Which of these equations should I use? Well, if you're given these data on Gibbs free energy formation, use this equation. If you know delta S and delta H, use this equation. It should be straightforward. There are a few more useful equations that you should know about. Whoa, look, K, that's our equilibrium constant, K. Delta G, spontaneity, and the equilibrium constant. There's a relationship between those. Now it's really confusing. How do I calculate delta G? Well, if you know your equilibrium constant, you use this equation. If you know delta H and delta S, you use this equation. And if you have your Gibbs free energy of formation, you use this equation right here. Another useful equation? No, this is standard state when you see the little 0 here. Standard state means 25 degrees Celsius and equilibrium conditions. So concentrations are at equilibrium. Non-standard state, notice there's no 0 here, or no not. It's a not. When we are not at standard states, we're not at equilibrium. So we have Q. Q is whatever the concentrations are in that moment, not the equilibrium concentrations. So Q, the actual concentrations, as opposed to equilibrium concentrations. Then we get our non-standard Gibbs free energy. Okay, Let's hide this for a moment. The last two equations, they are uniting thermodynamics and equilibriums. Now all of a sudden, we've got all these chapters coming together at once, and on the next chapter that we can even relate electrochemistry to all of this, and it all comes together and it's so nice and unified. Okay, last note on this, put it in red because it's important. This is what I talked about earlier, this equation right here. If delta SH is positive, greater than 0, and delta S is negative, less than 0, do you see that this equation right here, if this is positive and this is negative, we have a positive minus a negative is always positive, and the reaction is delta G is always positive, never spontaneous. If delta H is negative, we've got a negative here, and delta S is positive, greater than 0, right here, we have a negative minus a positive. That must always be negative. I hope you mathematically understand that. So delta G would always be negative in this case, and the reaction is always spontaneous. Now, if you have delta H and delta S either both positive or both negative, then the temperature is what defines spontaneity. If delta H and delta S are both positive, can you see you need a large delta T? Sorry, a large temperature to overcome the positive delta H to get a spontaneous reaction, because you want delta G to be negative for spontaneity. If delta H and delta S are both negative, then this is negative. A negative times a negative would be positive. This overall term would be positive. And it's the low temperatures, very small temperatures, that would give us an overall negative delta G. Okay. Moving on, we're going to do some practice problems now with all this information we just learned. We've got to remember spontaneity, exothermic, endothermic, entropy changes. What does this all mean? Okay, first off, I got these problems we're about to do from this website right here. And the solutions are at this website right here. So you can type in these websites and look for some more problems, because I did not include all the problems from those, if you would like. There are actually some very nice problems in there. All right, number one. This is just general, do you understand this? So we're going to check all the following that are true. And I want you to think about this. We know the sign of delta H, so that tells you if your reaction is endo or exothermic. You're given the sign of delta S. You have the sign of delta H, so you want to think about this equation right here to figure out, is it true that this reaction would always be spontaneous if delta S is positive and delta H is negative? Catalysts. You should remember that from the last chapter, kinetics, where this is kinetics too. Do catalysts change delta H? Would this reaction be more spontaneous at higher temperatures? You want to think about this equation right here. So if delta S is 71, would minus T delta S, with this being a positive number, if we increase temperature, will it become more spontaneous? More spontaneous would be more negative. The more negative delta G is, the more spontaneous the reaction is. Okay, this last piece, so no, it's not the last piece, part F, you want to look at this. I didn't talk about this before, so you're learning it right now. Delta S of the surroundings, that's not your reaction, that's the surroundings, what's outside of the reaction. Delta S of the surroundings is positive if a reaction is exothermic. So if you're giving off heat, the entropy, not of the reaction, but of the surroundings, increases. So exothermic reactions, entropy of what's around the reaction is increasing. So that's what you need to answer this question. Okay, is this true? Since O2 is the naturally occurring form of oxygen, S naught, the standard entropy is 0 for oxygen at 25 degrees Celsius. You got to remember this from chapter 6. Okay, H, activation energy of the forward reaction is lower than the activation for the reverse reaction. Is that true? That depends on delta H. You want to think about your activation energy curves, and if delta H is negative, does that mean reactants are higher or lower than products? And does that mean that your activation for the forward reaction is more or less than the activation for the reverse reaction? I'm going to put up these answers, so hopefully you've got your answers in there. I'll put the correct answers up. Okay, here are your answers. And part H, if you're confused, I just drew a real quick activation energy curve or energy curve. So this reaction is exothermic, delta H is negative, which means the products are below the reactants. Energy is on the y-axis, reaction progression or reaction coordinate is on the x-axis. So if products are lower than the reactants, then the activation energy, remember, is from your reactants to the top of the hump or from the products to the top of the hump. So because products are lower than the reactants, the activation energy for the forward reaction must be less than the activation energy for the reverse reaction. Hence, H is true. Alrighty. Another set of thought process questions. Now you just want to think on this one. This ammonium chloride dissolves readily in water. It just dissolves. So you got to think, is that spontaneous? It dissolved. It happened. If something happens, it's spontaneous. So whatever happened here, it did happen. It was spontaneous at 25 degrees Celsius. The solution gets cold, so you have to think, is this reaction endo or exothermic? Is this reaction endo or exothermic? I'm going to pause and put in the answers. So make sure you paused it. I'm pausing now. Okay, here are your answers. The beaker got cold, which means the reaction took heat out of the water. The reaction is endothermic, the process. We're going from a solid and then forming ions. We're forming NH4 plus and Cl minus, so entropy is increasing. Delta S is positive. For this last part, you have to look at your delta G is delta H minus T delta S equation. We saw delta H was positive, right there. Delta S was positive, right there. We have a positive minus a positive. This is not always spontaneous. It's not never spontaneous. It's not never, and it's not always. It's only sometimes spontaneous. And you have to figure out, would it be spontaneous when T is large or small? We want this piece to be bigger than this piece. So it would be when this piece is big, so higher temperatures. Now the actual height of how high the temperature has to be, we don't know exactly. We just know at 25 degrees Celsius, this definitely is spontaneous because it dissolved in water. There would be a temperature at which this ammonium chloride would not dissolve spontaneously in water. All right, another problem. You're given the molar heat of vaporization, delta H vaporization. And you're also given the boiling point. We want to find the entropy change, something about delta S. Okay, we've got delta H, we want delta S vaporization. So there's a special equation we have to use. And you're thinking, well, what's going on? When you are boiling, you're at equilibrium. So I don't know if you remember phase diagrams, the boiling line. So here's our nice little phase diagram. There's a T down there. That's not just a little line going below. Trying to fix that T, not having a lot of luck. In any event, all of these lines here are equilibrium between phases. So when we talk about boiling, that would be the equilibrium between the liquid and the gas phase. If we're talking about melting, we're at an equilibrium when we're melting. It's equilibrium between the solid and the liquid. And over here, we're at equilibrium between the solid and a gas. So boiling is equilibrium. We learned something a little earlier. At equilibrium, delta G is 0 at equilibrium. You have to memorize that fact. That tells you that delta G is 0 if you're boiling. Now we use this. Say what? Delta G is delta H minus T delta S, which has to be 0, which means we're just solving. Delta H is T times delta S. We'll solve that for delta S, which is the entropy of vaporization. We were given the boiling point. The temperature for this type of equilibrium would have to be the boiling point, which must be in Kelvin. We had Celsius. We have to get Kelvin. And the heat of vaporization we were given in kilojoules. You have to be careful now. We were given this in kilojoules per mole. If you left that in kilojoules, you'd have to have your entropy in kilojoules. Now the units are very important. Joules per mole Kelvin. That's the correct answer. You want to be very careful with the units that you use in these problems. Now we asked what's the entropy change for vaporizing 50 grams? Well, we know how many joules we would get for a mole. How about grams? Here we go. The entropy change for 50 grams of ethanol is 121 joules per Kelvin. We were keeping 3 sig figs here. 3 sig figs right here. Here we could have kept 4 sig figs, keep the answer up to the 10th place, and then at the very end we have to round to our 3 sig figs. Okay. Okay, another problem. Now on this problem, hold on. There we go. I knew something was wrong there. Okay. If delta S for this reaction is 425.1 joules per Kelvin, calculate the standard entropy for chlorine gas. Remember, entropy is not 0 when you're not at 0 Kelvin. Entropy is only 0 at 0 Kelvin for pure elements in a crystal structure. Okay, so you're just going to, for this, you just do products minus reactants equals 425.1. We have our products, we have our reactants. Pause, go ahead and pause. I'm about to show you the answer. You should pause. Here comes the answer. It's all worked out. Okay, so the entropy for chlorine, the standard entropy for chlorine gas, Cl2, is right here. And those are the correct units. Just always be careful. Notice entropy is always given in joules, joules per mole Kelvin. Enthalpy is typically in kilojoules. So whenever you use your equation delta G is delta H minus T delta S, you want to make sure that your enthalpy and your entropy have the same heat units, either both in joules or both in kilojoules. Be very aware. Be very aware. Very aware. Okay. Explain if the reaction or process is always, never, or only sometimes spontaneous, and whether that would be at high or low temps. So think about it, pause, I'm going to talk you through it. Delta H is negative. Delta S right here. It's not the S of chlorine, it's the delta S for the reaction. So you have to always read these questions very carefully. Delta S is positive, delta H is negative. So we have a negative minus a positive. Temperature is always positive. So if delta S is positive, T delta S is positive. A negative minus a positive is always, always, always negative. So this thing is always spontaneous. There you go. Okay. Calculate delta G for the reaction. Well, you just plug in your numbers. Go ahead and pause. I'm about to show you the answer. Just delta G is delta H minus T delta S. You have delta H right here. You have delta S right here. Make sure you convert delta H into joules or delta S into kilojoules. And use Kelvin. Standard means 25 degrees Celsius to 98 Kelvin. There you go. Okay, calculate K. Oh, what equation are we going to use for this? We got to find an equation. Oh, there's no equation there. These are problems. Is there an equation over here that, oops. Whoa. Oh, here's an equation. Look at that right here. Delta G is negative RT ln of K. T, temperature. Delta G, you're going to use, you're calculating delta G, which will be in joules. So you need, which R are we going to use? You need an R that has joules in it. And you're panicking, which R do I use? And you look at the equation sheet that you have, and look, there's an R with joules. Would make sense to use that value for R now, wouldn't it? In fact, that's always the R value that you use when you're dealing with anything with energy. So let's go back. So we're going to use the joules for R. And we're going to use delta G as negative RT ln of K and solve that for K. To get rid of logarithms, you have to use e to the power. So you solve for ln of K. We just plugged everything in here. Solve for ln of K, and to get rid of the ln, you have to do e to the power, which is kind of strange. So you have to do e to the raised to the 211.4, or 211. And this is the number you get. Okay. Oh, now we want the equilibrium constant at a different temperature. So don't forget to convert it to Kelvin. Same equation. So we know delta G. We just use the same delta G. We know R, 8.314. You don't need to use the 5 there. Temperature, convert to Kelvin. You can pause and put this in. I'm about to show you the answer. There you go. Okay. Last question. And remember, to get rid of logarithms, you have to do the inverse equation, which is e to the power. Oh, goodness. No, they used a different... Oh, sorry. This, we haven't learned this equation. Okay, you are not responsible for part E, but this is very similar to the equation ln of the rate constant is equal to negative EA over R times 1 over temperature, where we would have the activation energy here. But don't worry about this equation. However, the next question, if you were given, you calculate this, if you're given that the K for the reaction at 175 is this, now we have a new question. Explain why the equilibrium constant goes down. Notice it went down as temperature went up. We went from 25 to 175. And the equilibrium constant went down. It decreased. Use Le Chatelier's principle to explain that, noting that the reaction is exothermic. So you want to think through this. You can pause, and I'm going to talk you through it right now. So, exothermic, if heat or temperature increases, we want to get rid of some heat. Heat's on the right, so the reaction would be pushed to the left as temperature went up. If we're pushed to the left, the equilibrium constant should decrease, because equilibrium constant is products over reactants. Reactants are going up because we're pushed to the left. Products went down, K goes down, and indeed, K does decrease as temperature increases from 25 to 175. And there you go. There you go. That's it. Okay. And just make sure you do 1, 2, 3, 4, 5 problems. These are not mathematical problems. There's only one. This number 29 is very similar to number 3. Whoops. It's very similar to this one right here. So there's a little bit of math in these problems. Most of them are conceptual, just thinking about entropy going up or down, and delta G equals delta H minus T delta S. Okay, that's all, folks.